Today we'll start a new chapter, so we will now talk about measurable functions. So first we'll study some of your basic properties and definition of measurable functions. So X is a non-empty set and S is a sigma algebra. We'll work only with sigma algebra in future on X. Okay, so then you say XS is called a measurable space. That means it has all the structure necessary to define a measure. So it has a non-empty set and you have a sigma algebra, and so if possible one can define a measure on it. So an extended real valued function f on X is a function which takes values in R union plus minus infinity. So you allow infinite values also. Okay, so now definition. XS measurable space, F extended real valued function defined on X. We say that F is a measurable function if for every alpha in R we have F inverse of alpha plus infinity belongs to S. That is, set of all X in X such that f of X is strictly bigger than alpha belongs to S for every alpha in R. Okay, so then such a function is called a measurable function. So if X equal to Rn, we say that F is Borel measurable if it is measurable with respect to S equals Bn. It is Lebesgue measurable if it is measurable with respect to S equals Ln. So if you have the Lebesgue sigma algebra and the function is measurable, then you say it's a Lebesgue measurable function, and otherwise if it's if the sigma algebra is the Borel sigma algebra, then you say it is Borel measurable. Okay, remark. F Borel measurable implies, of course, F is Lebesgue measurable, but not the converse. Okay, fine. Okay, so proposition, first proposition, there's nothing sacred about the way we have defined measurability. So you have the following various equivalent forms. XS measurable space, F extended real valued function on X. The following are equivalent. One, for every alpha in R, f inverse of alpha plus infinity is in S, that is f is measurable. 2. For every alpha in R, f inverse of alpha plus infinity closed is in S. Then 3. For every alpha in R, f inverse of minus infinity alpha belongs to S, and for every alpha in R, f inverse of minus infinity alpha belongs to S. So set of all x such fx bigger than alpha is in S, that's a definition, but you could have also defined it by set of all x such that fx is greater or equal to alpha, set of all x such that fx is strictly less than alpha, set of all x such that fx is less than or equal to alpha. All these sets are in S. So each of these implies others, and therefore you could have defined measurability using any of them. So proof: 1 implies 2. So f inverse of alpha plus infinity is nothing but the intersection n equals 1 to infinity f inverse of alpha minus 1 by n infinity and since each of these is in S, intersection is in S, and therefore this also in S. So 2 implies 3. So f inverse of minus infinity alpha is nothing but f inverse of alpha infinity complement, and therefore this belongs to S. Let's say plus infinity always, because this belongs to S, so this complement is also in S. So 3 implies 4. F inverse of minus infinity alpha equals intersection n equals 1 to infinity f inverse of minus infinity alpha plus 1 by n, and therefore again this belongs to S, because by 3 each of this is in S and intersection is in S. And then 4 to 1 again by complementation, f inverse of alpha plus infinity is nothing but f inverse of minus infinity alpha complement, and therefore this also belongs to S, and consequently you have all these things are equal. Corollary: 1. XS measurable space, f extended real valued function which is measurable. Then for every alpha in R union plus minus infinity, we have f inverse of singleton alpha belongs to S. 2. U contained in R open implies f inverse of U belongs to S. Okay. Proof. So let us take alpha in R. Then f inverse of alpha is what? F inverse of alpha is intersection n equals 1 to infinity f inverse of alpha minus 1 by n infinity intersection minus infinity alpha plus 1 by n and since all of these inverse images are in S, countable intersection is in S, so this belongs to S. If alpha equals plus infinity, then you have f inverse of plus infinity equals intersection n equals 1 to infinity f inverse of n plus infinity, and again, so this belongs to S. Similarly, f inverse of minus infinity equals intersection n equals 1 to infinity f inverse of minus infinity minus n, and again this belongs to S. Okay, now if AB is contained in R, then you have f inverse of AB equals f inverse of minus infinity B intersection f inverse of A plus infinity, and therefore this belongs to S. Now every open set of U is a countable union of intervals, and therefore this corollary is proved. Okay, so now we give some examples. So let us take x equals Rn, then f x to R continuous and real valued function. I am not taking extended real valued function. Then f is both Lebesgue and Borel measurable, because U is f inverse of alpha plus infinity. This is the same as f inverse of alpha plus infinity, and this is an open set. F is continuous, so this is equal to open, and therefore which belongs to Borel and Lebesgue sigma algebras. Okay, so this is a very easy example. So example 2. So here we give a counter example. So here we proved in this corollary that f inverse of every singleton is measurable if f is measurable. The converse is not true. So f inverse of singletons, all singletons can be measurable, but still the function may fail to be measurable. So let us take the following example. Let us take E contained in 0, 1, E not measurable. So E does not belong to L1. Okay. Now you define f of x equal to x if x belongs to E, minus x if x belongs to 0, 1 but not in E, and minus 2 if x does not belong to 0, 1. Okay. So then let us compute what is f inverse of singleton alpha. So this is equal to r minus 0, 1 if alpha is equal to minus 2. Okay, so that's by definition. Then it's equal to singleton minus alpha if minus alpha belongs to 0, 1 minus E. It's equal to singleton alpha if alpha belongs to E. and it's equal to empty set if otherwise. So you can very easily verify all of this. So all of these belong to S. So all of these are, so every F inverse singleton alpha is in this. Now if you take F inverse of 0 infinity, so which are the only place where it takes positive values is on E, and this is equal to E, but this does not belong to L1, implies F not Lebesgue measurable. So measurability of singletons is not a test. Okay, then example again. So XS measurable space, and let A contained in X. Then you take F equals chi A of chi A. That means, so Fx equal to 1 if X belongs to A, and 0 if X does not belong to A. Okay, so this is a chi A. So what is F inverse of alpha infinity? Is equal to capital X if alpha is less than 0, A if 0 less than equal to alpha is less than 1, and empty set if alpha is greater than equal to 1. And therefore this implies that chi A equal to F is measurable if and only if A belongs to S. So whenever we deal with simple functions, we will deal with simple measurable functions. That means we are talking about characteristic functions of measurable sets. Finally, example 4. So XS measurable space, and Fx equal to C in R for all X in X. Then F is measurable, because if alpha is in R, then you have F inverse of alpha plus infinity equal to X if alpha is less than C, and is equal to empty set if alpha is greater or equal to C. Okay, so we have some examples of it. So now we will prove a proposition which is useful. Okay, so let XS measurable space, FG measurable real valued, not extended real valued functions on X. C is in R. Then F plus G, F minus G, CF, F plus C, FG are all measurable. Proof 1. Let C belong to R, then C positive. So set of all X in X such that Fx is bigger than C, CF of X is less than alpha. This is equal to set of all X in X such that Fx is less than alpha by C, and that of course is measurable because you know F is measurable. Similarly, if C is less than 0, then this set Fx less than alpha is set of all X in X such that fx is bigger than alpha by c, and again this belongs to S because of that. Now this is what is this? Cf less than alpha means minus infinity to alpha. Okay, open. So that is this is f inverse of minus infinity to alpha. So for every alpha this is measurable, therefore by the characterization we have, so this implies that Cf measurable. There. 2. Let alpha belong to R, and so now we want to look at set of all x in X such that fx plus gx less than alpha. We want to show that this is measurable. Again we are taking the minus infinity to alpha open as the test set. Okay, now this is equal to set of all x in X such that fx is less than alpha minus gx. That means you can put in a rational between fx and alpha minus gx, and therefore this is equal to union R belonging to Q, set of all x in X such that fx is less than R, intersection x in X such that gx is less than alpha minus R. So each of this is in S, and R is Q is countable, therefore this belongs to S. Okay, so f plus g is measurable. F minus g is nothing but f plus minus 1 times g. F is measurable, minus 1 times g is measurable by the first argument, and therefore this is measurable. Then 3, f plus c measurable. Because constant functions are measurable, f is measurable, sum of measurable functions is measurable, which we have already proved. So finally we want to prove the product. Okay, so let alpha belong to R and alpha positive. So set of all x such that f square of x, that is equal to set of all x in X such that fx is bigger than root alpha, or x in X fx is less than minus root alpha, and therefore this implies, so this will belong to S. If alpha is less than or equal to 0, set of all x such that fx is bigger than alpha is the whole of x, which belongs to S. And therefore from this we deduce, so this implies that f square is measurable. Now fg can be written as 1 by 4 f plus g square plus f minus f minus g square. Now f plus g is measurable, so the square is measurable. F minus g is measurable, so the square is measurable. The difference of measurable functions is measurable. Multiplying by a constant 1 by 4 is measurable, so this is measurable. Okay, so this proves this. Now remark, above proposition holds whenever given functions are well defined when f, g are extended real value. For instance, if f plus g not defined on at x, where fx equals plus infinity and gx equals minus infinity. You can't define f plus gx. So whenever, if the function is well defined, then the previous proofs will all go through, otherwise. So we will continue with the properties of measurable functions next time.